So, our speaker today is Luiz Gustavo Cordeiro, and his title, as you can see there, is Uniform Dimension from Gamma Monoids for Gamma Monoids and Applications to Graph Algebras. Please, Luis, go ahead.
Okay, so thank you very much to the organizers for the invitation to give this talk. This is based on joint work with Daniel Gonçalves and Roozbeh Hazrat in the last couple of years, and we'll just jump right into it. Okay, so our main idea was, well, as the title says, we generalize or adapt some notions from general algebra to monoids, and then our main focus was to apply that to graph algebra. So I'll just start by showing what our work on the theory of monoids was, and at the end we'll end up, how do we say, specializing that to graph algebras. So just some general monoids. We'll only consider additive monoids, a billion additive monoids with unit denoted by 0, and M will always denote such a one. So a monoid is just I didn't write the definition here, but it's just a structure with an addition, which is associative, and also commutative and has a unit 0. So basically a group without inverses, right? And we say that a monoid is cancellative if the cancellation law applies, and it's conical if it has that funny condition here. If the sum of two elements is 0, then both elements have to be 0. So for example, the natural numbers would be such a one. And it's a refinement monoid if it has this nice decomposition property here. Whenever we can write two sums as equal, then we can further decompose the terms of each sums into smaller elements in such a way that the terms, they are, well, they satisfy the decomposition. Sorry about that. It satisfies this property. Basically, we have this table where B is decomposing the terms in its columns, and A's are decomposing the terms in the same row. Okay. Here. No. Oh. How do I change now? Yes. And the algebraic preordering is defined as that. So an element is smaller than another one if the bigger one is a sum of the smaller one and another element of the monoid. So we will be mostly interested in the ordered structure of the monoid. The 0 is at the bottom of the monoid. All the other elements are on top of it, and if we add elements, we keep going up on the associate graph of the monoid. When the monoid is conical and cancellative, then that is actually a partial order on M. Okay, otherwise, it's just what is known as a preorder. And an ideal of M is a submonoid, which is also an ideal with respect to the algebraic preordering. Okay. So I'm not sure how do I skip slides. Here, go down. Okay. And two ideals of M, they are called independent if their intersection is trivial. Oh, now I don't have the, well, okay, I can try it now. Anyway, that is the same as saying that, well, at least for conical and cancellative monoids, that the elements of I and J are non-comparable. So that is, in this case, the ideas are independent if they satisfy both the property which is analogous to independence of ideals in the context of rings and also in the context of lattices. And the same for rings, an ideal of M is essential if it has a non-zero intersection with any other non-zero ideals. And if all non-zero ideals of M are essential, then M is called uniform. So in some sense, M does not have any non-essential proper part of it. And actually, we work on a slightly more general setting, which Hazrat actually introduced in one of his papers, which is that of a gamma monoid, where gamma is a group. So a gamma monoid is a monoid endowed with an action of a commutative group gamma. And we denote the action by a pre-superscript instead of the usual product notation. And then the gamma homomorphisms, gamma ideals, and all the gamma variants of the usual notions for monoids, they have their obvious definitions, right? So a gamma homomorphism is just a homomorphism between gamma monoids, which also respects the gamma action. The gamma ideal is both a ideal of the monoid, which is invariant by the gamma action, and so on. So I won't spend too much time listing those. All right, so the problem that we first attacked was just how to translate the notion of dimension to the context of monoids. So we adapt the definition of uniform dimension, which comes from Goldie's work on ring theory. And we say that the uniform dimension of a gamma monoid M is the supremum of all cardinals kappa, such that M has kappa many independent non-zero gamma ideals. Okay, so that can be thought as the largest, in some sense, independent subset which we can find inside M. And there is a invariance theorem for that as well, which is very similar to the dimension theorem for vector spaces, in the sense that if we have a conical refinement gamma monoid and two decompositions of essential ideals into uniform ideals as direct sums, then these direct sums have the same amount of terms. And then that can be related to the...
Sorry, you do not require that I be equal to J. So
no.
Okay.
No, we can have two essential ideals which are different among themselves, but if they are decomposed into uniform ideals, then the number of terms is the same.
Okay.
Okay. Yeah, we can always, well, in this setting, if we intersect the terms of I and J, we can probably find a smaller essential ideal, but they may be non-comparable in general. And the proof is quite similar to the dimension theorem for vector spaces. We just, up to some permutation, substitute all the terms of the I and the terms of the J step by step and show that the essential property is preserved. Okay.
Okay.
Yes?
Okay. So the essentiality is an ambience property.
Yes. It's an invariant.
Where uniformity is a standalone property, right? So the II
yes.
are uniform. Doesn't
yes,
matter.
The IIs, they are uniform if, as gamma monoids on their own, they do not have essential, non-trivial essential ideals. And
so it's
we have to be a little careful here, right? If we have an ideal of, or an ideal of M, then the smallest ideal is also an ideal of M. That's not too hard to show.
Okay.
Okay, so all these notions, they are well behaved.
Mm-hmm.
Yes.
Okay, copy.
Sorry. So you said this was introduced by Roozbeh Hazrat, right? In the 2012 paper, the classification of
Sorry,
fluid path.
the
Yeah,
audio is
you
not very
said,
good.
okay, am I audible now?
Yes,
Yeah, so you said these gamma monoids were introduced by Roozbeh Hazrat, right? In the 2012 paper, the classification of Leavitt Path Algebras.
yes.
But if I remember correctly, he introduced
Oh, he introduced
gamma
the
graded,
terminology, and I think
yeah, yeah,
that
gamma graded
monoids
I,
with
modules, right?
group actions were already considered before.
Yeah,
yeah,
but he introduced it in terms of it was gamma grading on the monoids.
no, I mean, the example is you take a graded ring graded by a group gamma, and then you
Right,
take the monoid of finitely generated projective,
Yes,
graded projective modules, gamma graded projective modules, and that is a gamma monoid.
yes,
So there
I
is a
see.
gradient on the ring, and the gradient on the ring induces an action of the group, not a gamma gradient, but an action on the monoid of finitely generated graded, gamma graded projective modules.
yes.
Okay.
Okay. Yes. So we, in this setting, right, we could have instead defined the uniform dimension of a gamma monoid as the number of factors of uniform factors in a direct sum, which is a essential essential ideal of M. However, the definition in green here is a bit more general because we can talk about we can differentiate different infinite dimensions, and actually, it's not too hard to show that all infinite cardinals, they can be realized as the uniform dimension of an appropriate gamma monoid. Okay, and we will see an example similar to that in a few slides. So there are, of course, some questions, right? So how does uniform dimension for even monoids with a trivial group action or gamma monoids relate to the original definition of uniform dimension of for rings or for modules? So in the second item, there is a possibility for the relation is the uniform dimension of M seen as a gamma monoid, the same as that of the Grothendieck group of M seen as a module over the universal ring generated by the group gamma. Okay, that's something that we have not worked on, and perhaps another answer would be
So,
the appropriate one.
so when you mean the Grothendieck group, you mean the group completion, right?
Yes, the group completion of M. Because we are working only on commutative, consecutive monoids, so it has a group completion, and then a group with an action of a ring is the same as the module, right? Yes. So it would be interesting to understand how if these two definitions they are really if they speak to each other in
So,
the
so,
way that we would expect.
so what the notion in the case of the second question, right? Yeah. So
Yes.
when they mention a module, what do you mean? Projective dimension? What kind of dimension?
Uniform dimension, which would be the same as the
Ah,
one we have in green here, however, with submodules instead of ideals.
ah,
So,
okay.
yes.
And that exists. That is well defined. I mean, because
Yes, that is well defined. That
you need
was
a
the original
conical
Goldie.
refinement, blah blah blah, and then
Yes. That is actually where we based our definition from.
I mean for a module on over the ring.
Yes.
Okay.
Yes. So we are in a quite different context, right? A module over a ring has an action of the ring on a group, and we have a group acting on a monoid. And usually the we're looking at additive monoids, so it's not really clear how to translate one of the contexts to the other ones. So that the second item would be the obvious question, the obvious way to construct a module from our setting. However, I'm actually not completely convinced that would be the right translation.
Okay.
Yes. Okay. And so since we are looking at independent ideals when we look at the direct sum, this naturally leads to the notion of annihilator of an ideal, which is the largest ideal which is independent to the original one. So the annihilator of a gamma ideal I of the gamma monoid M is denoted with the orthogonal complement notation, and it consists of all the elements of M which are non-comparable with non-zero elements of I, or either they are zero. In the conical and refinement case, that is the same as saying that the ideal generated by A is independent with I. And in the conical and refinement case, the annihilator of an ideal I is also a gamma ideal of M. And these two properties, they are actually necessary, especially the refinement one. In the non-refinement case, the annihilator of an ideal needs not necessarily be a gamma ideal of the monoid as well. And this annihilator construction, it satisfies a few of the usual properties of a complement, as this proposition states that for a family of gamma ideals of M, the annihilator of a sum is the intersection of the annihilators. The other property, that the annihilator of an intersection should be the sum of the annihilators of the terms, does not necessarily hold. Okay? And the second property states that the direct sum of the ideal and its annihilator is essential, so we do indeed have something that resembles a complement. And the double annihilator construction is a closure operator. And so we say that a gamma ideal I of M is regular if it coincides with its double annihilator. So it's we're basically translating the usual definitions from ring theory to our context. And we managed to prove a nice little theorem that states that if M is decomposed as the direct sum of an ideal and its annihilator, then the ideal has to be regular, but not necessarily the opposite. An ideal might be regular, but the whole monoid needs not to be decomposed as the direct sum of it and its annihilator. And here's an example of that. If M is a collection of open subsets of a topological space X under union, then it is a non-consecutive, actually, however, refinement monoid. And to each subset, the ideal, each open subset of X, the ideal it generates in the monoid has the, no, that is actually not the ideal it generates. However,
what's the monoid operation in M, in this M?
Union.
Okay.
No, actually, I'm wrong here. It should be intersection. Otherwise, yes, I misspelled here. It should be the collection of open subsets of the topological space X under intersection. Otherwise, we do not necessarily have an ideal here. Okay. So I need to fix that.
So the order goes the other way, right? If I take two elements and I add them, then I end up with a smaller element in the containment of sets order.
Yeah.
And but in the monoid order, it's bigger.
Yes, the monoid order is the inverse of the offsetting proof.
Okay.
Yes. But here I'm taking downsets. Yeah, so that's something that is a little different from now I need to be a little careful here. So for ideals, we need to have downsets, and they have to be submonoids. So sorry about that. No, it's really union, and then the order is the same. The order in the monoid is the same.
Okay,
Yes.
union, right? Okay.
Union, yes. And we can show with not too much trouble that the annihilator of the ideal induced by an open set is the ideal induced by its usual complement in the algebra of open sets of the topological space X. And so the double annihilator of an ideal U is the annihilator induced by the regular or regular enclosure of the open set, the interior of the closure of the original open set. So in particular, the ideal generated by an open set is regular if and only if the open set itself is a regular open set. So, for example, if we take the unit interval with the usual topology and the first half of it, that is a regular open set, and then the ideal it generates is regular. However, the whole monoid given by the open subset of X is not the direct sum of the ideal and its complement. It does not contain, well, because the right-hand side does not contain any open subset, which contains the point 1/2. Okay. And from that, we move to the case of graph algebras, which is mainly motivated by the algebraic Kirchberg-Phillips question. So we have a theorem which was proved, which says that in some certain manner, the K-theory of a Leavitt Path algebra classifies the Leavitt Path algebra completely. In the case that E and F are finite graphs. Sorry? Well, not completely.
The determinant. I thought you were asserting that the conjecture was true. No. Okay. Yeah, so you put the determinant there. Okay. Thanks.
Yes. So that is the point. The restricted version has this determinant condition on the adjacency matrices of the graphs, right? In the case that the algebras are pure infinite simple, and we have this condition here, which is not really trivial, then any isomorphism or unitary isomorphism between their A0 groups induces an isomorphism between the Leavitt Path algebras. So that is quite particular to the case, the algebraic case. And in the C-star case, we can drop these conditions. So the natural question is, can the determinant hypothesis be dropped as well in the algebraic case? And that is still a very much open question, which motivates a lot of work nowadays. So I'll just throw out some of the definitions that I'll be using. A graph consists of a set of vertices, a set of edges, and two maps, source and range, which map edges to vertices. And we'll be focused mostly on the row-finite case. So a graph is row-finite if for every vertex there are at most finitely many vertices which have these finitely many edges which have this vertex V as its source. And a vertex V is regular if it is the source of at least one edge, and it's a sink if it is not the source of any edge. And so the letters E and F will always denote row-finite graphs from now on.
Yeah, a fastidious comment is that the definition of regular vertex is wrong if E is not row-finite. So you
Yes.
should have assumed row finality.
Yes, I should assume row finite.
First.
Right. Yeah, from now, after defining row finite, I assume just row finite. Yes. However, yes. And so we can describe the K-theory of the Leavitt Path algebra just looking at the geometric properties of the graph itself. And that is the construction given by the graph monoid associated to a row finite graph, which is given here. So the graph monoid associated to a row finite graph E is the free monoid generated by the vertices of E, subject to the relation that every vertex is equal to the sum of the vertices which are directly connected to it. So it's the sum of the ranges of the edges which start at the vertex V. For every regular vertex V. For sinks, we do not have any relations. And so the this graph monoid defined here is actually the positive cone of the K0 group of the Leavitt Path algebra of the graph E. And from that, I will not really define what the Leavitt Path algebras are. I saw that some previous talks that have considered them, but then I will focus mostly on giving the geometric description of algebraic properties of the graph monoid, knowing that it can be translated to K-theoretic properties of the Leavitt Path algebra.
Yeah, so here the assertion that it's the positive cone assumes that ME is cancellative, right? Or, you know, if the algebra is purely infinite simple, then ME is the same as K0, except that it has an additional neutral element. So it's not exactly cancellative. So the image of ME is the positive cone. But the map might be
it is isomorphic.
Yeah. It's not an isomorphism. It might not be injective. So, for example, M of the graph with one vertex and two loops is not zero, but its group completion is zero.
Yes. Yes. That is right, assuming the ME is cancellative. Okay. All right. So we can restate the classification conjecture, or the algebraic Kirchberger conjecture with the graph monoids, which says that if E and F are finite graphs with purely infinite simple Leavitt Path algebras, is a unito isomorphism between the graphs, and then unito will be specified a little further, are the Leavitt Path algebras Morita equivalent or isomorphic. And we know from the general literature that the graded structure of the Leavitt Path algebra actually plays an important role in its algebraic structure. So that motivates us to look for graded versions of all these notions. And here's a definition that was introduced by Hazrat and a co-author whose surname I cannot really remember now, which is the talented monoid Juan Li, right?
Yeah.
Yes. Which is the talented monoid of the graph. So the talented monoid of a finite graph is the free monoid, which is generated by the vertices of P, however, of the graph. However, they are marked by integers as well, subject to relations which are very similar to the ones in the graph monoid. However, you can always substitute a graph V marked with well, I like to think of the marking as a time where we arrive at the vertex with the sum of the ranges of the edges starting at that vertex, however, at the next time, at I plus 1 for every regular vertex. Then this talented monoid is both Z-graded, because we have these markings on the generating set by elements of Z, and it's also a Z-monoid with the action which simply takes a vertex V marked with I and adds an element of Z in its marking. And similar facts hold for talented monoid. It is, again, in the cancellative case, the positive cone of the...
this one is always cancellative.
Yes. It is the positive cone of the graded K0 group of the Leavitt Path algebra of E. And it is actually a particular case of a graph monoid, which is constructed from the original graph as well, by also adding markings to the vertices and the edges of the original graph, which are very similar to the construction of the talented monoid. So we substitute given a graph E, we substitute its set of vertices by Z many copies of the vertices, and all the edges, they have the same source, or rather, for every edge, we add an edge in this new graph with the Z markings, which connects the same source and range, however, from a time K to the next time K plus 1.
One of the two is wrong. One is K, one is K plus 1.
It should be K here in the source, not K plus 1. Yes, it goes from time K to time K plus 1. So another typo there. And then the graded classification conjecture asks whether the analogous of the classification conjecture in the non-graded case holds.
But the hypothesis of purely infinite simple is not part of the conjecture. I mean, this conjecture is for finite graphs, period, with no specific property such as being purely infinite simple.
Yes, I probably just copied this one here. Yes, because when we have Z gradings and Z isomorphisms, then much more of the algebraic structure is preserved. So that is right. So just for finite graphs, if the question asks whether the Leavitt Path algebras are Z-graded isomorphic, if and only if there is a unitary Z isomorphism between the talented monoids, seen as Z monoids. And the unit is considered to be the sum of all the vertices at time 0. So even though this question is still very much open as well, our idea is to show that supposing that the conjecture should be true, that much of the graded algebraic structure of the Leavitt Path algebra can be encoded in the Z structure of the talented monoid, and also verify how those relate to the geometric properties of the graph E. And then I'll need to add some terminology for subsets of the vertex space of the graph E. A path is just a sequence of edges which meet source to range. The source of a path is the source of the first edge. The range of a path is the range of the last edge. So I'm reading paths left to right. And a cycle is a path which has the same source and range. And a subset H of the vertex space of E is hereditary if it has this condition. So it says that if there is in another case, if it has a path which starts at H, then its range also belongs to H. And it is saturated if it has the opposite condition. Whenever we have all the vertices which can be connected to H, that to a vertex V belonging to H, then this vertex V also belongs to H. So the set of hereditary saturated subsets of E0 is a lattice, and it corresponds to the lattice of Z ideals of the talented monoid in the following sense. Every vertex in E0 is seen as the element of the talented monoid given by the same vertex indexed at the time 0. And for every subset of E0, we can thus generate an ideal in the talented monoid. And so with this identification of vertices as elements of the talented monoid, the map which takes a hereditary saturated subset and generates its ideal in the talented monoid is a lattice isomorphism with a quite simple inverse. So anything we can say about the hereditary saturated subsets of E corresponds to something we can say about the Z ideals of TE. And actually, we have a similar isomorphism between the hereditary saturated subsets of E and the Z-graded ideals of the Leavitt Path algebra as well. So our first problem was now to take the notions which were introduced in the beginning of the talk for Z monoids at the graph level. So we consider there the annihilators of ideals of a Z monoid. So in our case, when we have the talented monoid of a graph, what do the annihilator of an ideal of the talented monoid corresponds at the level of the graph? So we have an answer for that, and for a hereditary saturated subset H of E0, we let H perp be the set of vertices of E0 for which there is no path starting at V. So it should be the set of vertices V, for which there is no path starting at V and ending in H. So they are the vertices which cannot be connected to H via path. Then H perp is hereditary and saturated, and H double perp consists of all the vertices V of E0, such that every path starting at V can be extended to a path ending in H. And our first theorem in that regard is that the perp of a hereditary saturated subset of E0 corresponds precisely to the annihilator of the ideal induced by that hereditary saturated subset. And so, in particular, we can also classify the hereditary saturated subsets which correspond to the regular ideals of the talented monoids. They are precisely the hereditary saturated subsets which coincide with its double perp, which is described right here. And the second theorem classifies the essential ideals of the talented monoid in terms of the subsets of E0. So given a hereditary saturated subset of E0, the ideal generated by the subset is essential if and only if it is cofinal in E, in the graph.
So does that mean it's so it's as a subset of the vertices regarded as a partially ordered set with a path order? It's cofinal in that sense that every
vertex can be connected to H.
Okay.
So yes. So in these terms, the ideal generated by a hereditary saturated subset is essential in the talented monoid if and only if every vertex can be connected to H via a path. Okay. And then in particular, the talented monoid is uniform, so it has only essential ideals if and only if every hereditary saturated subset of E0 is cofinal. Again, in the sense that every vertex can be connected to that. And so we say that a hereditary saturated ideal of E0 is uniform if its ideal inside the talented monoid is uniform. So that is the same as saying that every hereditary saturated subset of H now is cofinal in H. And here is just the last phrase is just a rewording of the uniform property. And actually, the isomorphism between the lattice of hereditary saturated subsets of E0 and the ideal of TH, it respects the talented monoid construction in the sense that if we get H and restrict the graph E to get the reduct, which has only vertices of H and edges which connect its vertices, then the ideal in TE is actually isomorphic via a natural isomorphism to the talented monoid of this reduct.
So there is, I mean, TH is defined not just by the vertices of H, right?
Yeah,
but
it is the reduct of the graph E to the set of vertices.
Yeah, so, but on the left-hand side, I mean, you have the ideal generated by H0, right? Inside of E0.
Yes.
H was in E0. It
Yes.
was not a graph.
Yes.
So maybe you mean a subgraph, but then the thing generated by is generated by H0, right? Or
yes, I can't write down now, so. But
no, but just to understand. Yes. I mean, what you mean.
Yes, TH is actually T of the graph constructed as follows. Take the vertex set as being H, and the edges of this graph are the edges of E, which connect vertices of H.
Okay. And
so it's the full subgraph of E with vertex set H. Yes?
Yeah. So it's like, yeah. So it's the full subgraph generated.
Yes. The full subgraph generated by H. So we're using a shorter notation here.
Yes. Yeah.
And then from those considerations, since we can classify the uniform ideals of the talented monoid geometrically, and also the essential ones, right? So this theorem is somewhat funny because it does both at the same time. We may describe the dimension of the graph E in the uniform dimension of the talented monoid in geometric terms. The uniform dimension of the talented monoid of a finite graph E is a number n, if and only if E0 contains n pairwise disjoint uniform hereditary saturated subset of E0 whose union is cofinal. That is just a direct translation given by the previous theorem. And as a corollary, we can see that the uniform dimension of the Leavitt Path Algebra in the original sense by Goldie, which I did not really state in this talk, is greater than or equal to the uniform dimension of the talented monoid of E. And I suppose this should almost always be a proper inequality. However, we have equality if we do some variations on Goldie's original definition of uniform dimension of a module. And here, the uniform dimension is seen as of Lk of E of the Leavitt Path algebra is seen as a left module over itself, not over the field K.
So the Goldie's definition is analogous to that for monoids with annihilators. And
yes, so it's analogous to, where is it? Here, right? So it's analogous to the green one. So the uniform dimension of a module over a ring is the supremum of all cardinals kappa, such that the module has kappa many independent non-zero submodules. Okay. However, the reason I suppose these inequalities should be almost always strict is because the ideals of T, they correspond to bilateral ideals of the Leavitt Path algebra. So we did have something that is stronger.
But okay, I suppose you can make the same definition.
Yeah.
Bilateral idea for bimodules, and then
yes, that's what I say. And also graded, right? We have to have the grading as well. So perhaps with some modifications to Goldie's definition of dimension of a module, we get equality. It's not hard to show that. But with his original definition, it should be a
okay, but the definition applies. I mean, the definition is well defined for any graded algebra.
Yeah.
Okay. So it will be it's equal to the graded Goldie dimension or something. Graded two-sided.
Yeah,
Goldie.
Which I could not find in the literature, but should not be too hard to come up with.
Okay. Thanks.
Okay. So our final results, they give us a geometric classification of the ideals of the talented monoid, or maybe not so much as a classification, but as much as we could reasonably expect to get. So first we notice that every vertex X may be written, well, if E is a finite graph, then every element of the talented monoid may be written as a sum of vertices indexed by integers, which are either sinks or belong to a cycle. Basically, we just apply the relation which defines the talented monoid a bunch of times, letting a vertex be substituted by the ranges that it can look at several times, and by the pigeonhole principle, they should start repeating at some time. So we get vertices which are in a cycle, or if we cannot apply the relation anymore, it means we have vertices which are sinks. So we consider the collection of all these vertices, which are either sinks or that belong to a cycle. And we have a pre-order, which I think that's what Guilherme was talking about, the path order on the space of vertices. That is defined as a vertex V being greater than or equal to a vertex W if there is a path which connects V to W. And then further definitions, an exit of a cycle alpha is a path B whose source is a source of an edge in alpha and whose range is not. And the return of an exit beta to the path alpha is another path gamma which connects the end of the exit beta to a vertex in the path alpha. And then we have our supposed classification of the ideals, which says that the indecomposable ideals of the talented monoid, that is, those ideals which cannot be decomposed as a direct sum of proper ideals, are precisely the ideals generated by the vertices in this collection, which are sinks or below trace cycle. And moreover, such an ideal generated by such a vertex is simple if and only if either V is a sink or it belongs to a cycle such that every exit has a return. Equivalently, the ideal generated by such a vertex is simple if and only if it does not belong to a cycle which has an exit without a return. And any Z ideal I of t decomposes as a sum of these indecomposable Z ideals, where the sum ranges over the maximal elements of the set of vertices which also belong to the ideal I. And actually, a conjecture that I did not write here is that the uniform dimension of the ideal I should equal the number of terms which this sum has. Actually, it's smaller than or equal to that, but perhaps it could be equal, say, if every vertex is either a sink or belongs to a cycle such that every exit has a return.
Is this one of the results in this Revista Iberoamericana paper?
Sorry?
Is this one of the results in this Revista Iberoamericana paper? Or
No.
maybe you were not. Okay.
No, this is a result in our last paper, which I think it was accepted for publication, but it's available in archive now, which is uniform ideals of talented monoids of graphs. We have a similar result in the paper in Revista Iberoamericana, but it has to do with the colorings of the ideals. We get something quite similar, actually, to this one, but it's stated in terms of colorings of ideals.
Okay.
Yeah. And as a corollary, every ideal of the talented monoid is regular if and only if no cycles of E have an exit without a return. And this geometric condition was already known to be the same as the Leavitt Path Algebra of E having only regular ideals. So indeed we have a very strict dictionary between the ideals of the talented monoid and the ideals, or rather the graded ideals of the Leavitt Path Algebra. And the last result that we managed to obtain is that for a row-finite graph, the talented monoid is decomposable in the sense that it is the direct sum of two proper Z ideals, if and only if there is a non-trivial hereditary saturated disjoint subsets H and K, such that every vertex can be connected by a non-zero and finite number of paths which start at V and end in H or in K. So as a corollary, TE is indecomposable if and only if the Leavitt Path algebra of E is indecomposable as well. Oh. And here's
Okay.
This is where I am. Thank you very much. The references are here. I didn't write all of them, but then that is the paper where all these results are stated and proved. Maybe in a slightly different order here, and the references therein. And also this paper has some of the things that are presented here. Thank you.
Okay, thank you. Thank you very much. And thank you for citing a paper I'm a co-author of also. Yeah, so are there any more questions apart from the many that I already asked? Okay. Well, so, and what are your plans in this line of research? What comes next?
Where is it? Here.
In this business of the talented monoid and
Yeah, so it would be quite interesting answer this question, which I did not have time to work on recently, but it's always good to know if.
but I mean, this doesn't this business with the Goldie uniform dimension and inequality, that in order to change it to an equality, you need to consider, well, of course, graded modules, but also bimodules. Maybe the word there should be bimodules, judging from that, or not.
Yes, but I think it's important to really have a counterexample if we use his original definition. So I guess we're talking about this one, the corollary, right?
Yeah.
It should not be too hard to get an example with a proper inequality. So that would imply that we need to have a graded version for
so I had misunderstood you. So you said this is almost always an inequality, but I thought you had lots of examples because you said that, but you still do not know a concrete counter
No,
example.
I don't have. Yes, because his definition. I don't have an example where it's a proper inequality. Yes, but if we do the modifications on the notion of uniform dimension, then it's not hard to prove that we do get an equality.
Okay.
Yeah. And also, we started looking at the groupoid version of some of these results. And it would be also interesting to know whether we can do something similar, changing Z by another group gamma. So there are some works on the asymptotic theory of graphs, but changing the group Z, which represents time in some sense, by some other group. So that does not seem to be a very well-developed area, and I suppose we could translate much of what we have to that context as well.
So by the groupoid setting, you mean you take the Steinberg algebras, graded Steinberg algebra.
Yeah.
And so instead of TE, you would take what the monoid or projective finite generated graded projective modules.
Yes.
Yeah, because much less is known about that monoid. I mean, a lot of work has been put into the talented monoid, but for the monoid of a general Steinberg algebra.
Yes, the definition of the analogous of the talented monoid is already quite hard. It's called the type semigroup, or the graded
type semi, yeah.
of the monoid. Yes, so we have worked a little bit on it in a previous paper, but it is harder to deal with. However, we hope that things can be translated. Yeah.
Okay. Well, thank you very much for a very nice talk. So if there are no more questions from the audience, I will stop the recording.
Thank you very much.